Well, so we learned about different types of passive components like filter, couplers, power dividers, T junctions. Now a special case, mass termination. So, for example, let us say you are using a branch line coupler, you are utilizing 3 ports, port P1, port P2 and port P3, but isolated port you are not using. So, should you keep it as it is? If you just keep it open circuited, then there will be reflection and the properties of branch line coupler it will change. So, port 4 isolated port, it should be mass terminated, or we should connect one 50 ohm load to port P4. Similarly, mass termination we used in many other situations also. Now, at millimeter wave frequencies, realization of mass termination is really challenging, because of the reactive contribution of different guiding system, means bends or discontinuities. So, whenever we are using, let us say, a 50 ohm resistor, you can use for example one SMD resistor. So, one end you have to solder it to your transmission line. What about the other end? It should be grounded. So, the second end, when you are grounding, obviously you will be using some metallic via, and metallic via, it is one sort of discontinuity, it will give you some inductance. So, you want to realize a 50 ohm, you have a 50 ohm SMD, but when you connect it to circuit, it is not just 50 ohm, it is 50 ohm with some additional reactance. Then how to obtain this mass termination at millimeter wave frequencies? At lower microwave frequencies, this inductance value is so small, usually we neglect it, but at millimeter wave frequencies we can't. So, let me give you one example and how we can compensate this inductive effect. So, in this example, it is realized in BCB in 45 micrometer thick BCB substrate. You can see the top plane metal, we have CPW line basically, and this black rectangle, it shows rectangular metallic via that connects the top plane metal with bottom plane metal, and you can identify the central conductor. Now, for this BCB or in silicon or gallium arsenide technology, how do we design a resistor? We can't use SMD, we use nickel chromium alloy. Usually the fab lab, they will give you a standard thickness for that nickel chromium and standard resistance per centimeter. Then you have to choose a proper dimension. So, you know that resistance, it depends on length and the width. So, accordingly you have to select your length and width to realize a given resistance value. So, in this picture, this RW and RL, they shows the length and width of that nickel chromium section, we call it thin film resistor, and right hand side you can see one long black line, and on that we have 3 vias. Instead of 1 via, they are using 3 vias to reduce the inductive effect. Now, if I simply take the RL and RW, so that its equivalent DC impedance, DC resistance is 50 ohm, then if we measure it, input impedance, it becomes different because of the inductive vias. So, for example, typical return loss is inferior to 20 dB above 50 gigahertz, and this variation is due to ground path inductance due to the via. So, what is the compensation technique then? So, for this shunt inductance, we can use shunt capacitance to compensate or nullify their effect. How to realize then the shunt capacitance? The from open stub, from transmission line theory, we know that if we place one open stub with a microstrip line, it will give you some shunt capacitance. The same technique is used here also. Now, the thing is that you have to calculate what is the equivalent inductance given by the grounded via, then you have to calculate what is the equivalent capacitance you need, and for that what is the equivalent length of the open stub. But instead of this calculation steps, practically what we do, we simply use a full wave simulator. Full wave simulator will give you the S parameters, and then you choose the width of your open stub and simply tune the length, just one parameter. In a few simulation step, you will get the desired result. So, in this picture you can see they are using these two open stubs of width SW and length SL. They will give you the required shunt capacitance. So, practically the resistance value, it is chosen a little lower than the required one. For example, this particular example, let us say the required value is 50 ohm, then they started with 38 ohm for this nickel chromium resistor, and if they need, let us say 70 ohm, then they started with 61 ohm, and now you see the result. If you have inductive contribution, S11 will be very poor. Now, since they have compensated it at some given frequency, let us say at 50 gigahertz, then for 50 ohm load, it is showing this black line, S11 is 27 dB. So, in reflection loss, return loss is more than 27 dB. So, it is quite good, and for 70 ohm design, even it is better than 40 dB at the design frequency. So, it is quite good, but without this compensation, if you start with just 50 ohm, the loss value is below 10 dB, it is quite high. So, this is a narrow band design. Now, wide band design is also possible. There are several techniques to make it wide band. I will show you one example. So, in this particular example, they used another shunt arm. How they realized it? So, one single 50 ohm, they are realizing by using two shunt resistors, nickel chromium thin film resistor. So, one is grounded by using chain of vias, and the second one, it is connected to one open stub, which will give some shunt capacitance. So, without this shunt arm, this shunt additional arm of dimension, it is given 250 micrometer by 60 micrometer, which will give you equivalent resistance of 158 ohm. This is the DC resistance. So, without this shunt arm, it shows 71 plus J30 ohm and 100 plus J53 ohm at 100 gigahertz and 160 gigahertz respectively. And now, with this compensation, so this is designed by using a full wave simulator, the required length, width of nickel chromium thin film resistor and the open stub for this given 59 ohm. Then it becomes matched over wide bandwidth. You can see here the simulated result over 0 to 160 gigahertz. So, in this simulation also we are considering a fabrication tolerance of plus minus 10% dimension. Now, you see the result. So, left hand side it is showing S11. So, actual S11 value for this design given by the solid line always below minus 20 dB. So, 25 dB from 0 to almost 150 gigahertz. Now, considering plus minus 10% fabrication tolerance, even then this dashed line and dotted line, even then it you can say it is below 20 dB over 0 to 160 gigahertz. And now, right hand side it is showing the real and imaginary part of input impedance as seen by this microstrip line. So, imaginary part, it is approximately 0, you can see this line, you can follow this line, it is within plus minus 5 J, and the real part, it is very close to 50, it varies between 50 to 60. So, overall S11 is below 20 dB. Now, we have discussed about different passive components, and in some of the design we are using different types of waveguiding structures. So, not only that, when we go for any millimeter wave systems, we in the same system different components can be it can use different types of waveguiding structures. Some components may use microstrip line, some components can use rectangular waveguide, some components can be designed in NRD. Now, all of this we have to integrate in one single systems. So, obviously, we need some adapters. One microstrip line components, if I want to connect it with one rectangular waveguide system, we need one microstrip to rectangular waveguide transformer or transition we call. Now, whenever we design any transition, we mainly face two problems. First one, mode matching, and the second one is impedance matching. For example, microstrip to rectangular waveguide. In microstrip line, it supports quasi TEM. We know the electric field configuration, but inside rectangular waveguide we use TE10 mode. It is transverse electric mode, which has different mode property. So, we have to somehow transform this quasi TEM mode into TE mode, and not only that, it should be matched from both microstrip feed point and also rectangular feed point. So, let me give you some popular examples of these different types of transitions involving different types of guiding structures at millimeter wave frequencies. The first example is coaxial to microstrip line and coaxial to CPW transition. Frequently we use for measurement purpose. So, in coaxial cable, if you recall that always we use TEM mode, we never use TE or TM mode, we want only monomode propagation. So, for TEM mode, electric field, it is from the central conductor to outer conductor. So, they are perpendicular to magnetic field lines. Now, we want to connect it to a microstrip line. So, coaxial line, it supports TEM mode, microstrip line, it is also quasi TEM mode, and it also has electric field component which is perpendicular to ground plane. So, simply we can then connect one coaxial line to microstrip line directly. Coaxial line, let us say its impedance is given 50 ohm, microstrip line impedance is also 50 ohm, then directly it can be connected. Only thing is that the central conductor, it should connect the strip of this microstrip, and the outer conductor, it should be soldered to ground, and we used only one half of this, so that it can excite the microstrip line, because if I use both half of this coaxial cable, then they will nullify this the effect of the microstrip line field configuration. So, this is the structure showing the conducting parts only. Similarly, we can also excite CPW line. So, for CPW line, you see electric field, it starts from the signal line and terminates into ground. So, we can again use this TEM mode of coaxial line to excite quasi TEM mode of CPW line. Let me draw the field diagram. So, for a CPW line, let us say this is the signal line and this is the ground plane. Now, we have electric field lines from signal line to ground. Now, if I compare these field lines with that of a coaxial cable, this is the central conductor of coaxial cable, and let us say this is the outer conductor of coaxial cable, and inside we have TEM field configuration. So, you see, then simply we can use this part of coaxial cable. We can connect this part of coaxial cable directly to CPW line. We will be soldering the central conductor to the signal line and this outer conductor, this part, to the ground plane, and then this component of electric field, it will excite this component, and this right hand side component, it will excite this component. So, we do not have any problem due to field matching, and in both of these two different guiding system we have quasi TEM mode, and if the characteristic impedance of both CPW line and coaxial cable is 50 ohm, in that case we can directly connect it without using any impedance transformer. Next, coaxial cable to waveguide, how we can excite it. Now, inside coaxial cable we have TEM mode, and inside rectangular waveguide we have transverse electric mode. In this case we have to use a mode converter, and this is done by using the fringing field of this coaxial line. So, inner conductor, you can see this is the cut wave view, this is side view. So, wave inside rectangular waveguide is propagating from left to right, and at left hand side we are using a shorting plane which is lambda g by 4 away from the central conductor, midpoint of central conductor, and the central conductor, its top point, it is soldered on the broad side of broad side of this rectangular waveguide, and then the fringing field inside the coaxial cable, when it terminates, it opens into rectangular waveguide, we have fringing field inside the rectangular waveguide, and that fringing field, it excites the TE10 mode inside rectangular waveguide, and because of this lambda g by 4 short termination, we do not have any wave propagation on left hand side. You can say somewhat like if any wave propagates in left hand side, then it will be reflected from this short plane, and they will be, it will be out of phase, and in the front side we do not have any reflecting surface. So, simply it will propagate. So, top view how it looks, you can see only the central conductor soldered on top plane, and this dotted line, it shows the slot etched in the bottom plane. So, power is coupled through this slot into rectangular waveguide. We can also design coaxial cable to SIW transition. If you recall, SIW is substrate integrated waveguide. So, for SIW, inside we have dielectric, and for coaxial again we have dielectric, and otherwise all the principles are very similar. Usually it is a narrow band design, typical bandwidth 5 to 10%. We can improve the bandwidth by using some matching pin. So, simply we use some metallic via inside the rectangular waveguide for matching purpose to improve the input reflection coefficient, and in that way we can cover a single band of 40% bandwidth. I am showing you another example, microstrip line to rectangular waveguide excitation at millimeter wave frequencies. So, here what is done, the microstrip line geometry, it is fabricated on a printed circuit board substrate. So, this is showing the microstrip line geometry. Just below the microstrip line, in the ground plane of the microstrip line, we have one aperture, we call it ground plane aperture. So, power from microstrip line is coupled to waveguide through this ground plane aperture. So, this shaded part, orange color part, it is showing the ground plane metal, and this dark orange color part, it is showing the top plane metallization of printed circuit board. So, you can see the termination of this microstrip line, it is terminated into one open stub, radial stub, and before that, just before ground plane aperture, we have two matching stub, open circuited stub. It is used for controlling the input impedance. Now, how it is placed inside the rectangular waveguide, you can see this is showing right hand side pictures, it is showing the side view. So, this ground plane aperture, it opens inside the rectangular waveguide, and above, just above the strip, we have a back cavity, and the cavity height, it is lambda g by 4, but it is not very sensitive to this lambda g by 4, just like the previous one. It can be a little less or more than lambda g by 4. Then right hand side, you can see the microstrip line. So, from microstrip line, power is now coupled into rectangular waveguide, and here it shows measured performance of a back to back transition. That means, from microstrip line to rectangular waveguide, again from rectangular waveguide to microstrip line, and this is the measured S parameters. The first example over 40 to 50 gigahertz band, and you see the S21 is quite good for these two transitions, including a section of rectangular waveguide. So, its mid band loss is just 2 to 3 dB for two transitions. And next measured example, it is on quartz substrate for the PCB. It is from 90 to 100 gigahertz, and over this band loss is below 4 dB for these two transitions. So, similar transitions also possible using finite ground CPW line. Now, excitation of substrate integrated waveguide from microstrip line, from CPW line, and from coaxial cables. There are different techniques reported in literature for millimeter wave applications. So, for all of these 9 designs, so the very basic things, 2 points. One point, we have to convert the mode, and the second point is impedance matching. For example, for this first design, you can identify left side, we have one substrate integrated waveguide structure which supports TE10 mode, and right side we have 50 ohm microstrip line. So, rightmost it starts with 50 ohm, and they are designed in one single substrate. So, that means a single board, a single PCB is used for the same design, and now 50 ohm microstrip line is terminated into TE10 for field configuration, field matching or mode matching. For microstrip line, we have the perpendicular field components. Inside rectangular waveguide, again we have perpendicular field components. So, we do not have any problem due to field matching. However, we have problem due to impedance matching. So, that is why we need one impedance transformer. So, how it is done here, you can see a linear tapering used here. Usually, the length of this linear tapering is lambda g by 4 at the center midpoint, mid band of frequency, and by using a full wave simulator, simply you can tune the terminating width to obtain a better S11 and S21. Usually, this design is wide band having more than 40% bandwidth. So, similar design is possible, and right hand side, instead of open circuit here, they starts with a short circuiting wall. So, it somewhat looks like how we feed rectangular patch antenna. It is using some inset feeding, and rightmost one, instead of just simply inset, it is actually capacitively coupled. We are using a one finger type capacitive coupling. Next, CPW to SIW transition. So, in all this example, you can see we are not using conventional CPW. Usually, we avoid it at millimeter wave frequencies, because a simple CPW line, it sits on substrate, dielectric substrate, it will excite surface wave mode. Rather, we prefer boxed CPW or ground backed CPW line. So, right hand side, and you can see the vias of the ground backed CPW line, and left hand side we have the SIW structure. Now, in SIW we have perpendicular electric field components, and right hand side for the CPW we have both microstrip line mode and CPW mode. For CPW mode, you remember that it is inside the slot and it will be then parallel to top plane, and for the microstrip line mode it is perpendicular. So, in the same direction as of TE10 mode. So, again we have good field matching. The only thing is that we have to obtain good impedance matching, and that is being done here by using short circuited slots termination of different shapes. In next row, this is example of coaxial to SIW transition. This first example actually we discussed for rectangular waveguide. You can see the coaxial central conductor shown by this black dot, which is lambda g by 4 away from the shorting wall, and two matching pins they are used to improve the input impedance matching. And instead of a shorting wall, we can also use one open circuited wall. In this case, you can see the central conductor is directly soldered to one open circuited end. So, we do not need any extension, but again we are using similar matching vias here, and right hand side again a shorting wall, but with different geometry for impedance matching. Next is NRD. NRD, it can support both longitudinal section magnetic and longitudinal section electric. In longitudinal section magnetic mode, in the propagation direction mainly we have the magnetic field components. So, for LSM11, if I concentrate on electric fields they are maximum on the central plane and they are parallel to the ground plane. If you recall, we are using a dielectric slab in between two ground planes. So, now if I want to excite this LSM11 mode by using a rectangular waveguide, so right hand side it shows the TE10 field configuration of rectangular waveguide. We have the electric field perpendicular to broadside. So, simply then we can place a rectangular waveguide on top of this, so that electric field they are in same direction. So, then it shows the top view actually. I am showing a cutaway view. So, you see the LSM11 mode, it will have parallel electric field component parallel to ground inside this, and then you have to turn this rectangular waveguide to have the electric field of TE10 mode in same direction. We do not have any problem due to field matching. Next problem is impedance matching, because left hand side we have transverse electric mode, right hand side we have longitudinal section magnetic mode. So, how it is done? Rectangular waveguide, it is air filled. So, you see its dimension we are using a tapering slowly varied, and right hand side we have the dielectric slab, it is now extended into rectangular waveguide, and again we are using a tapering, and by controlling the tapering length we can tune the input impedance. Now, how to excite LSE11 mode? For longitudinal section electric, if I look at electric field configuration, you see it is coming from left hand ground plane, then going into propagation direction. From right hand side it is coming, then on mid plane it is in propagation direction. So, we can't simply place a rectangular waveguide on top of it, because we have both left hand side and right hand side component and they will cancel each other's effect. So, we have to use a different scheme. Rather than electric field, we can excite this LSE11 mode from any aperture on the ground plane and using a let us say magnetic field coupling. Here this is the geometry. So, instead of TE10 we are again turning it to have the TE01 mode, and left hand side it is terminated by a short plane similar to coaxial to rectangular waveguide. It is lambda g by 4 away from this midpoint, and you can see this rectangular waveguide section, and right hand side we have the NRD section. Now we have coupling through magnetic field from the rectangular waveguide to LSE mode of this NRD guide. Again we can we can tune the tapering length for proper impedance matching. So we have discussed about the different types of passive components, mass termination, and also transitions frequently used at millimeter wave frequencies. Next we will start some active device and then its application, typically electronic switch, because electronic switches is very popular for controlling the performance of wireless systems, and then some example of millimeter wave systems. So for today let us stop here. Thank you.